In this video, we're going to look at how we can multiply complex numbers and see how the relationship between complex numbers and vectors is different here than it has been for simple addition. The multiplication of complex numbers is not the same thing as a scalar multiplier for vectors. It's definitely not the same as a dot product. It's definitely not the same as a cross product. It's something new. And it deserves some exploration, and we're going to do that through some sample calculations to start. If we take two complex numbers, written out in their real plus imaginary component form, then the multiplication works essentially the same way as it would work with polynomials or anything else where we can distribute the product. So if we take the 3 times the minus 1, that's going to give us part of our solution, part of our value. And then if we take the 3, or let's take the 2i, the 2i times minus 1, we just add all of these together and repeat the same process for the 3 times the 5i, and again for the 2i times 5i. And in some sense, we're not doing anything special right now. We've just expanded out this product using standard rules of products of sums equals the sum of the products. Where it gets more interesting is when we look at the resulting values, we have an I times I term. And again, remember, I squared is defined to be minus 1, so that we get I equaling the square root of negative 1. And when we just rewrite each of these terms individually, with that in mind, minus 2i plus 15i, notice here we have 10i squared. Now what we're going to do with that is not keep having higher and higher powers of I. That gets turned into a negative 1, and so that becomes an all-real term now. As an all-real term, it can get gathered with the negative 3 we had before, so we have negative 3 minus 10, so we're going to have negative 13, and then we're going to have plus 13i. So an important note about this product with complex numbers is when we start with a complex number, we end up with something that can be represented as a complex number as well, a combination of real parts and imaginary parts. Let's do a few more for practice. We're going to take this product here next, and we'll do this a little more efficiently. We'll just do the products in our head. So 1 times 1 is 1, 2i times 1 is 2i, we'll have 1 times negative 2i, and then 2i and negative 2i is negative 4i squared for that final term. We do that same translation, that I squared is equal to negative 1, and rewrite a little bit here. We're going to have 1 plus, actually the 2i and negative 2i cancel each other perfectly, so they actually disappear, and we're going to be left with positive 4 with the double negative here. And so this just equals 5, and to represent it as a complex number, implicitly we can slide a 0i in there, though it's optional. So we have a product of two complex numbers that ends up actually being totally real, no imaginary component. Now it turns out that's not a coincidence. If we look at these two values here, they're identical except for the sign of the complex, sign of the imaginary part. And when we flip the sign of the imaginary part and end up doing these products, this is more advanced than you need for today, but if anyone's seen some complex numbers before, these numbers are called complex conjugates of each other. They're the same number except with the sign of the imaginary part flipped, and there's interesting properties when we add or multiply complex conjugates. That's enough for a little aside. Let's take a look at a couple more examples. Next up, if all is real, so if we had two real numbers, 3 and 7, but we're thinking them as complex, does that break any rules that we know from before? Well, fortunately no. 3 times 7 is 21, and then every other term that we get is 0, or worst case, 0i squareds, and 0 times anything is still 0, so we do get 21. So 3 times 7 is still 21, even with the 3 and 7, we're thinking them as being possibly complex numbers. Now, what if we had a pure imaginary times something else? That doesn't turn out to be a big problem either. We just do what we did before, only there's only 2 expansions we have to do for the multiplying into the brackets. So we're going to get 12i plus 24i squared. Oh wait, I squared is negative 1 So we're going to get 12i minus 24, and just for style, no practical reason, we tend to write the real parts first. So we typically put the negative 24 plus 12i, just so we know the real parts kind of in that first coordinate system, first coordinate set. Now just looking at all of this, especially like this first one, 3, 2i, we get 7 plus 17i. Like, it's not obvious what's happening here. If we take a look at those numbers, how does this relate back to the original values? Not clear at all. This is going to require us looking at the graphical side again though, and I think we'll see something happening. Let's take some sample calculations and see what they look like graphically. If we take the first complex number here, 1 plus 2i, that's down here, and if we multiply it by 2, let's take that number here. If we do the algebraic side, z1 times z2, well, multiplying by 2 is actually pretty easy. It's just 2 plus 4i. So that puts us at 2, 4i. Oh, it's exactly here. Interesting. So multiplying by 2 just stretched out the vector, kind of like a scalar product. Let's take a look where we have an imaginary multiplier here. So same initial vector, we'll do that still in blue. 1 plus 2i. And then we're going to multiply by not 2, but by 2i's, which is up here. And if we do that calculation, z3 times z4, we're going to get 2i's. I'm going to take a bit of a shortcut here. We have 2i times 2i, that's 4i squared, or minus 4. So negative 4 plus 2i puts us up in this corner here. And how can we see that relationship? Well, take a look and see if anything jumps out at you. To me, it certainly would not have been obvious at a first pass, but if you consider angles from the axis here, and again, we're aiming towards complex exponentials. Those had some relationship to sine and cosine, so angles are not totally crazy to think here. But we think angles, and we imagine this little angle here. Let's call it the angle of Z1. Sorry, Z3 in this case. And then we take this angle here, which is 90 degrees. That's the angle of Z4. This is a little triangle. I'll try to draw it more cleanly here. Z4, that's what we're trying to write out in small form. And then we take the angle, that's the new thing that we just built here, the angle of Z3 times Z4. Well, again, I'd want to verify this, but this looks like around 60 degrees. That was around 90. And when we multiplied, we ended up with 90 plus, oh, hello. That angle was equal to the angle of Z3 plus the angle of Z4. Now, does that work back here? Is that plausible? Absolutely. We had one angle that was 60 degrees-ish. It's not exactly, but ballpark 60. That was Z1's angle. And the Z2 angle was just 0 because it was just flat along the real line. When we multiplied them, we got this angle plus 0 angle, so we got that angle for Z1 times Z2. We could have said, though it wouldn't have been necessarily unique, that this is the angle of Z1 plus the angle associated with Z2. So this is not a proof by any stretch of the imagination. This is just a maybe, and yes, in fact, yes. Let's take a look at two further examples just to see if we can make this more concrete and nail that down and see if it still makes sense. So using our same color scheme as before, the first two vectors are in blue and red. So Z1 is blue and it's 1 plus I, and Z2 is 1 minus I in red. And if we were to use the logic we just went through, well, the Z1 thing here is up by 45 degrees. The Z2 is down by 45 degrees, so we should get something along the axis here. We're going to want to talk about the length in a second, but let's just make sure that the angle is correct for that. Z1 times Z2 is going to equal 1 times 1 is 1. Then we're going to have plus I, minus I, and then minus I squared. And that actually is equal to, these guys cancel, and we get 1 minus I squared, but that's 1 minus minus 1, which is much better known as 2. plus 0i. So sure enough, this line that we just drew here out to 2 is what we get when we multiply z1, z2. What if we change it up a little bit and make things a bit bigger? Let's go minus 2 plus I, it's our blue line, minus 2 plus 2i is up here. And then in red, minus 2 plus 2i again. Interesting, okay, I'll try it with the same point. Let's make it look a little different so we can actually see both lines there. There we go. If we multiply those, what we're claiming is, well, the angle that we got for both of these is 3/4 of a circle. That's right, three quarters of a half circle, 3 pi over 4. And so if we add those together, we should get to 6 pi over 4, which would be straight down if we did it right. So my claim would be that our answer has to lie in the negative imaginary axis if this angle thing works. Well, let's find out. Z3 times Z4 is equal to minus 2 times minus 2 is plus 4. Then we have minus 4i and minus 4i's and plus 4i squareds. I squared, same as minus 1. And then if you check what we get, we have a plus 4 and a minus 4. Those cancel. That and that all cancel. And then we end up with negative 8i, which is in fact what we get for this part here. So, complex multiplication, or the multiplication of complex numbers, seems to involve the angle of the two complex numbers in the complex plane. Real and imaginary axes, angles, all this stuff here. Feels like there's some relationship to trig going on here. The thing that's also true, though it's less obvious, is that not only is the angle added together to give us the new angle, the other element here is not just when we multiply we add angles, but also the lengths. So if I take a look at the length of Z3 as a vector, it would be the square root of negative 2 squared plus 2 squared. Think of it as a vector with components. That would equal the square root of 8. And also Z4 would have a magnitude of the square root of 8 because it's the same thing. And when I multiply them, the lengths multiply and I get a length of exactly 8 just in the direction of minus I. So we're going to get some lengths multiplying and angles adding as a real substructure for everything we're doing when we multiply complex numbers. Let's just summarize that here. If we take Z1 times Z2, when we multiply them, the magnitude of Z1 times Z2 is going to equal the magnitude of Z1 times the magnitude of Z2, and the angle of Z1 times Z2 is going to equal the angle of Z1. Sorry, these guys are usually written more horizontally than I've done them here. Let's draw real formal, like straight lines and all. There we go. This is the angle of Z1 times plus the angle of Z2.